You know when you look at a snowflake and you just wonder, how does something so complex form so perfectly? Or what's the deal with a diamond? What really makes it so different from a simple grain of salt? Well, it turns out nature has a secret language, a hidden geometric code it uses to build pretty much everything. And today, we are going to crack that code.
So let's start with that question. What do a diamond, a snowflake, and a tiny grain of table salt actually have in common? I mean, on the surface, they seem completely different. But deep down, at their core, they're all built using the exact same set of rules.
And the answer is a hidden geometric code. It's like an invisible blueprint that nature uses over and over again. And this code doesn't just dictate their beautiful shapes, it also controls all of their unique properties. All right, so here's our roadmap for this explainer. First, we're going to uncover the 7 fundamental blueprints that all crystals are based on. Then we'll look at the 14 different ways you can arrange atoms within those blueprints. After that, we'll dive into the language that governs it all, symmetry. And finally, we'll see how this code gives materials their incredible superpowers. You know, every great building starts with a blueprint, and it's really no different in the atomic world. But here's the wild part. Nature, in all its incredible complexity, only uses 7 of them. That's right, just 7. Every single crystal ever discovered, from a microscopic mineral to a massive geode, is based on one of just 7 fundamental shapes. We call these the 7 crystal systems.
Okay, so it all starts with some pretty simple geometry. The first 3 systems are the easiest to picture. They're all based on a perfect box with 90-degree angles. The only thing that changes is the length of the sides. You start with a perfect cube, where all sides are equal. Then, if you stretch one side, bam, you get a tetragonal system. Stretch a different side, and now you've got an orthorhombic system. Simple, right?
So what about the other 4? Well, they just take this idea and run with it. They're what you get when the angles start to shift away from that perfect 90 degrees. This creates even more complex and beautiful shapes, like the hexagonal structure of a snowflake. So we have our 7 blueprints, but a blueprint is just an outline, right? The really interesting question is, how do you arrange the atoms inside that blueprint? This adds a whole new layer to our code. And get this, it turns out there are exactly 14 ways to do it. Not 13, not 15, just 14. These 14 arrangements are known as Brevet's lattices. Think of it this way. If the crystal system is the shape of the room, the Brevet's lattice is how you arrange the furniture inside it. But the rule is, it has to create a perfectly repeating pattern in every single direction. It's all about total perfect order. Let's go back to our good old cube to make this crystal clear. Within that 1 cubic blueprint, you can arrange atoms in 3 distinct ways. You can have a simple cubic lattice with atoms just at the corners, or you can stick an extra atom right in the middle. That's called body-centered. And finally, you can put an atom in the center of each of the 6 faces, and that's a face-centered lattice. Each of these arrangements creates a totally different material with different properties. Okay, so we've got 7 systems and 14 lattices. But why these specific numbers? Why these shapes? It's not random. There's an underlying rule, a universal law that explains why the code is written this way. And that law, well, it's just beautiful in its simplicity. It all comes down to one elegant, fundamental principle: symmetry. It's the rule that dictates which shapes are possible and which ones just aren't. You can almost think of it as the grammar of nature's geometric language. And symmetry itself is built from a few simple actions or operations. The 2 big ones are reflection, does it look the same in a mirror, and rotation. Does it look the same after you turn it a certain amount? Okay, let's make this super real with a quick experiment. Here's our cube again. Imagine we put a little dot on one of the top corners, just so we can keep track of where it is. Now watch this. We're going to rotate that cube 90 degrees around its center axis. The little dot moved, sure, but the cube itself, it looks identical to how it started. That's a symmetry operation. The object changed its position, but it appears totally unchanged, and that is the magic of symmetry. But this isn't just some abstract geometry puzzle, this hidden code of systems, lattices, and symmetry. It has huge consequences in the real world. It's what gives materials their amazing superpowers. So we've seen that a crystal can have reflectional symmetry and rotational symmetry.
The really cool part is that you can combine these simple rules in all sorts of ways to describe the total symmetry of any crystal out there.
So the big question is, how many unique combinations of these symmetry rules are even possible? How many different sets of rules can a crystal have? Well, the answer is 32. These are what we call the 32-point groups. And this is the core concept. As Dr. Mahmud Sefannaser explains it in our source material, these 32 combinations represent every single possible class of crystal symmetry that can exist in the entire universe. It's a finite, universal set of rules.
And here is the big payoff. This is why it all matters. That final symmetry code, one of those 32 possibilities, determines almost everything about a material. It's why carbon atoms arranged in that face-centered cubic lattice create a diamond, the hardest natural thing we know. It's why the specific crystal structure of silicon allows it to be a semiconductor, which powers, well, everything. The code is the superpower.
So where does all this leave us? We've cracked nature's code. We get the blueprints, we get the arrangements, and we get the rules of symmetry. The big question is no longer just about discovering what nature has already made, but what we can now create. If we know the code, can we actually start writing it ourselves to design the